In the section before, what we saw was network arbitration with respect to CAN bus. In this particular section, we're going to dive deeper down into CAN bus. We're going to look at CAN bus data frames, also called packets, and see what the different parts of those packets are and the various functions of those parts. In that way, we'll actually know at a bit and byte level what's going on in CAN bus. So what I'm going to do is introduce you to CAN 2.0a standard CAN data packet. Now, what is a standard CAN or what is 2.0a? Isn't CAN bus all throughout? Not exactly. We'll get into the different flavors, so to speak, of CAN bus later on in the course. But right now, I want you to just know CAN 2.0a and another one I'll show you just now. This is called standard CAN. This is the first one that they came out with, standard CAN. And the data packet looks like this. Now, I'm going to discuss this in a bit, but what I want you to also know is that there's something called CAN 2.0b or extended CAN. And this is what the data packet looks like. Looks almost the same, doesn't it? Well, the major difference in this, there are several differences, but the major one to know is this part here. We'll get into what the identifier does, but in CAN 2.0a, it is an 11-bit identifier. In CAN 2.0b, which is extended CAN, it's a 29-bit identifier. So the main difference between A and B, between standard CAN and extended CAN, is this identifier. There are some other smaller differences that I will discuss later in the course, but keep in mind that it's 29-bit. Now, for the purposes of keeping things streamlined, what I'm going to do is stick to CAN 2.0a or standard CAN when I'm discussing the whole data frames and packets and how CAN bus works on a message level. I'm going to stick with this throughout this section. And later on in the course, as I said, I'll discuss 2.0b and also something called CAN flexible data rate. So just browsing here, you'll see, the notation that I'm using is, you see a small block like this is 1 bit. This is 11 bits. I'll tell you what DLC is. This is the data byte section. This is something called CRC, end of frame, and so on. There are different sections and each section has its own purpose. Let's go to the next slide and break this data frame down. So we have the exact same thing here is right here. So CAN 2.0 standard CAN, this is what a typical data packet looks like. What are these different sections and what the heck do they do? What's their purpose? First one is arbitration. This section here is, you see, it has 11-bit identifier, is also known as message identifier, but it is simultaneously used for arbitration as well. Network arbitration that we looked at in the previous section, and we'll show you at a byte level, this 11-bit identifier, how it does network arbitration. Then we have this next section, which is the control section, or control field. This is data. This is the actual data that is embedded in the packet that has to get around the network. For instance, if we're talking about, again, the automotive industry, what'll be in here is, engine temperature, engine RPM, door lock status, the actual data. Then there's something called CRC, cyclical redundancy check, and then there's a ACK or acknowledgement, and something called EOF or end of frame. Let's get a little deeper into it. SOF, start of frame. At the start of every packet, there must be one bit that is an SOF or start of frame bit. Then there's arbitration. We're going to be spending a lot of time on this section here, this part of the data frame, because by far it's the most important part of this data frame. It does some complex stuff that we need to understand CAN bus. Then there's the control. If you want to send user-defined functions in here, data, this is totally user-defined. CAN bus, this protocol specification, doesn't specify what data and in what format it goes in here. If it's integer or 8-bit or 9-bit or floating points or unsigned integer or what, it doesn't specify anything. It just says there can be anywhere from 0 to 8 bytes here. 1 byte, 2 byte, 3 bytes, all the way up to 8 bytes. It's variable depending on how the device that sends it is set up. Then there's cyclical redundancy check. If you know about Modbus, you'll know about a CRC. There's a 15-bit CRC. A cyclical redundancy check is a calculation that's done on the frame, on the preceding bytes or bits in the frame, and then stored here. And then when this frame is received by the receiving device, the cyclical redundancy check is done again. The calculation is done and compared with what it receives to know if it's valid or not. If it's the same, it's good. And then there's acknowledgement. We'll get into that a little later on. And finally, end of frame. So there's SOF, start of frame, EOF, end of frame. There's some other bits at the end called IFS. We'll look at that much later on, and not that important. And in the remainder of this section, we're going to be pulling apart each of these sections and saying exactly what they do and how they do it. In the remainder of this section, what we're going to do is look at each field, each arbitration, the arbitration field, the control field, the data field within that data packet, and then go into detail and see how it fulfills its purpose. Just before that, before we could get into that, especially for the arbitration field, which happens to be our message identifier, we must understand the electrical characteristics, and especially what's a 1 and a 0 on a CAN bus network, what they are. So this diagram just shows 3 devices connected to our 2-wire CAN bus network. So this is a device, this is a device, this is a device. The devices just happen to be broken down into main control unit, CAN controller, CAN transceiver. Okay, but it's a whole device. Now you'd notice here these 2 labels, CAN H and CAN L. And CAN bus uses differential signal transmission, much like RS-485. Whether the CAN bus network has a logic 1 or logic 0 on it is determined by the difference in voltages between this CAN H and CAN L. CAN H actually stands for CAN high. This is the high wire. CAN H, CAN high. And CAN L stands for CAN low. Good, let's look at some electrical characteristics, some voltages. So this graph here shows it's a voltage against time, and it shows voltages first of all on the CAN high wire and also on the CAN low wire. This here, you're seeing this says logic 1 recessive. What does that mean? Now CAN bus is a little quirky in terms of electrical characteristics. It's a bit upside down. When both wires have 2.5 volts on it, it's actually considered a logic 1. So logic 1, when CAN H and CAN L, CAN high and CAN low exactly have 2.5 volts on them, so the voltage difference is 0 volts. 0 volts actually means a logic 1. See, kind of upside down. If no devices are transmitting, for instance, let me just go back here. If none of these devices are transmitting on the network is said to be in an idle state. In an idle state, it remains in the logic 1 state with CAN high and CAN low both at 2.5 volts. So then when you look at the difference or the difference in voltages, it's 0, right? If both are the same voltage. So let's go back here. So if both are 2.5 volts, 2.5 minus 2.5 is 0, that's 0 volts. In CAN bus lingo or language, it's known as the recessive bit. All right, so logic 1 is a recessive bit, they call it. Logic 0 is expressed here. This is logic 0 right here. So in other words, the voltage goes from logic 1 to logic 0, is where CAN low is pulled down to 1.5 volts and CAN high is pulled to 3.5 volts. So 3.5 minus 1.5 is 2 volts. So it says it here, logic 0 is CAN high is 3.5, CAN low is 1.5, so the voltage difference is 2 volts. And this is known as a dominant bit. So logic 0 is known as a dominant bit. So remember these things, logic 1 is recessive, logic 0 is dominant. And this is how essentially CAN bus on these wires, they express logic 1 and logic 0 as voltages. Big idea here. There's something very important that I want you to understand. Here's our graph again. Burn this into your memory. There's a rule, and this rule is enforced by the electrical characteristics of the CAN bus network and those 2 wires. This is it. If any device on a CAN bus network is driving the bus to logic 0, no other device can drive it to logic 1. It's electrically impossible. So let's go back to our diagram at the start. If this device here is transmitting and it's transmitting a logic 0, this device and this device can't transmit a logic 1. They won't be able to transmit a logic 1. Once this guy grabs the bus here and it starts with a 0, if they transmit it or 1, each of them transmit a 1 at the same time, the 1 gets clobbered, it disappears. It's why logic 0 is called the dominant bit and logic 1 is called the recessive, because logic 0 dominates logic 1 on the network from an electrical standpoint. From this point onward, what we're going to do is look at each of these different parts of a standard CAN 2.0a message frame and then break them down. See what their functions are, how they do what they do. And we're going to start with this one here, the arbitration field or message identifier. I had shown you in a previous lecture and told you that this serves two purposes. It's really called the message identifier of the message, but it's also used for network arbitration. So it's a message identifier, it's an 11-bit number, and it serves two functions as I had mentioned before. The first is to uniquely identify the message type. As you would recall, I said that in CAN bus, the various devices don't have their unique address that identifies them like in Modbus or Ethernet or TCP/IP. What is uniquely identified are the message types, the messages. So the messages have IDs, and those IDs are not the IDs of the senders or receivers of the information. Message identifier, it must be a unique number that identifies a particular message type. And then it also sets the priority of the message. Now, how exactly does it set the priority of the message? What's the rule? Well, it's a very simple rule. The lower the value of the message identifier, the higher the priority of the message. So this means that when an engineer is planning a CAN bus network, the message identifiers must be chosen so that they are unique, and also they must be chosen in a certain way that the lower valued message identifiers go to higher priority messages within the network. Again, using an automotive example, what's a higher priority message? Well, what about an engine light coming on saying that there's an engine problem as opposed to a door lock closing? Door lock closing will actually be a much lower priority than the engine. Remember this, burn this into your memory. The lower the value of the message identifier, the higher the priority of the message. Let's say I have message type 1 and message type 2. Two different messages. Now, it doesn't mean two different devices, two different message types. What exactly is a message type? The type of message? Well, it could be, for instance, using automotive again, this message type 1 could be a message type that comes from the engine that has RPM and, for instance, oil temperature in it. And message type 2 could be coming from the body control module that sets the status of a sliding door open or closed. So different message types for different areas in the vehicle and different modules in the vehicle. So let's say there are two message types, message type 1 and message type 2. Message type 1 has an identifier of this here, which is decimal 134, and message type 2 has this identifier here, which is decimal 144. Obviously, message type 1 has a higher priority than message type 2. And this higher priority or difference in priority is what comes into play when there are network collisions to say what is a higher priority than another. And it will allow messages of lower value and therefore higher priority to take precedent over these messages here, which are of lower priority. So that's how the network arbitration happens at the byte level in terms of priority. So let's start getting into a deeper view of how messages are transmitted on the CAN bus network. Getting very specific now, we're going to be using this diagram in a few of the lectures to come, right? Starting with this one. So it just shows three different devices on a network, 1, 2, and 3. These I'm just using 1 and 2 and 3 to refer to them. They don't have the address of 1, 2, and 3. Devices on a CAN bus network, they don't have unique addresses. So most of the time on a CAN bus network, there aren't going to be collisions. They'll just be normal transmission. And I want to tell you what I mean by normal transmission. Let's just use an example. So node 1 sends this. This is our example from before. Node 1 sends this, which is a message of type 134, the identifier is 134. Node 3 sends this, which is 144. Let's say this one is going to transmit, and it first checks for bus activity, and if the bus is in an idle state, it will then send its message. And it'll send the message and then stop. And let's say 1 second after that, or 1 millisecond after that, number 3 here sends its message, which is this here, which is of message identifier 144. It then sends it, it transmits, and it's fine. This guy transmitted, and then some time passed, the bus became idle, then this guy transmitted. And everybody's happy. The messages went out on the bus, they were received, everything is fine. So that this message here didn't collide with this message here. So the arbitration function of the message identifier in this case really wasn't used. The arbitration function of the message identifier itself comes into play when there are collisions, when one has to win the bus over the other. But if the transmission that I just described took place, no one has to win. It just so happened this guy transmitted when it was idle, it became idle again, and this guy transmitted and everybody was happy. So most of the transmission on a CAN bus network takes place like that. And of course, just as a reminder, remember I said, going back here, that our device will always check to see if the bus is idle before trying to transmit. And what does idle mean? Idle means logic 1 or recessive. So before a device transmits, it will check the bus to see that logic 1 is on the bus, which will indicate inactivity. It will then send or start to send. So that's an idea of normal, quote unquote, normal CAN bus messages flying back and forth on the network. In the next slide, we will look at what happens when let's say this one checks the bus and says inactivity, and this one checks the bus and says inactivity at the same time, and then they decide to simultaneously transmit their messages. That's where the priority of our identifier field comes in and network arbitration takes place. So in the last lecture, we actually saw that most of the transmission on a CAN bus network will not take place with these collisions. Most will take place without collisions, which is a good thing. However, there will be collisions. In the previous section where we dealt with network arbitration at a high level, I showed you how when there is a collision, one or more of the nodes, the CAN bus nodes, will back off a certain amount of time until they test the bus again to see if there's any bus activity or if it's gone idle, right? And the ones that will back off are the ones with the lower priority. The ones with the higher priority, the one with the highest priority would continue transmitting. So it's non-destructive collision detection. In this video, I'm going to dig deeper into that. I want to show you at the byte level, at the bit level, what happens that enables this non-destructive collision detection. So let's use an example as usual. Love examples. An example from the previous lecture is where we had node 1 and node 3. Now in the previous lecture, node 1 transmitted and then node 3 transmitted. There was no collision. In this one, we're going to create a scenario where number 1 and number 3, both of these nodes, they both check the bus at the same time, see it's idle, and then they both transmit at exactly the same time. And essentially what we're going to use is our two examples, previous examples. Node 1 has the higher priority because its message identifier is lower in value, and node 3 has the lower priority because its message identifier is higher in value. So in a collision, node 1 would win, essentially, but we want to see how exactly that happens. Now, something to note, let me just go back here. CAN node is transmitting the message identifier part. What it does, it will send a 1 or a 0, whatever bit it wants to send, onto the bus. Then it would read back the value of the bus to see if that bit was sent properly. That's one of the important points when we're looking at our non-destructive collision detection. So we're going to look at it here. So data packet collision, node 1, this is the message identifier. Node 3, this is the message identifier. And you notice I have value seen on bus and value that each node attempts to transmit, because sometimes a node will transmit a bit, but the value seen on the bus would be different because if it's not able to transmit it. So let's say in this scenario, the SOF or starter frame has already been transmitted. So now both nodes on the CAN bus network are about to transmit their message identifiers. So we're going to start from the start here, right? Both of them have in common in their message identifier 0 as the start. So node 3 transmits 0, node 1 transmits 0. They both read back the bus and see 0, and they said, oh, well, we're fine. Let's transmit the other bit. Same thing happens again. 0 and 0. Value seen on the bus is 0. No problem. Third bit, no problem. Everybody is happy. Node 1 continues to transmit, node 3 continues to transmit, because what they have transmitted, the bit, they read it back and they say, oh, that's the same one I transmitted, I'll keep on transmitting. There we go again. Node 1 transmits a 1, node 3 transmits a 1, and they both read back a 1 and say, oh, fine again, let's go again. 0, then 0, and they both continue transmitting, not noticing that there's a collision taking place. They just keep on transmitting. Then this happens. Node 1 transmits a 0, node 3 transmits a 1, because look, right here is where there's a difference in the message identifier because this is of a higher value. This has a 1 right here, this has a 0. That's what we're seeing right here. So now node 3 transmits a 1 and reads back the bus and says 0. Say, whoa, wait a minute, something is wrong here. I just transmitted a 1, but it's 0, but I read back a 0. So what happens? This happens. Node 3 stops transmitting because what it sends on the bus is, when it reads it back, doesn't agree. So it stops transmitting and node 1 continues to transmit. Notice that node 1, its packet, its bits aren't destroyed at all. Node 1 doesn't even know or even isn't even aware of node 3 and the fact that it was transmitting at the same time. It just is oblivious to it. Node 1 just essentially clobbers node 3 bits and it continues transmitting along its merry way. And that's why we call it non-destructive. The packet from node 1 doesn't get destroyed. It continues transmitting. So why is it that when this node 1 transmits a 0 and node 3 transmits a 1, it ends up 0? Remember in a previous lecture, I told you that if the bus is driven to logic 0, it can't be driven to logic 1 simultaneously. It can't be driven to logic 1. Right? So remember, logic 0 is dominant, 1 is recessive. Once there is a node, a CAN bus node, driving the bus to logic 0, it can't simultaneously be driven to logic 1. So 0 is dominant. Once the node is transmitting a 0 and pulling CAN high to 3.5 volts, pulling CAN low to 1.5 volts, this one can't be transmitted. So node 3 stops transmitting. Now, if there are other nodes simultaneously transmitting as well, they will stop if their identifiers are higher. So node 1 wins the battle. This is how non-destructive collision detection takes place at the bit level, at the byte level. This is how the message identifier, which is also our network arbitration field, does its arbitration, handles the collisions. This is a really, really important point. I think it's the most important point about CAN bus and CAN bus activity on the network, something for you to understand in a concrete way. So that's non-destructive collision detection at a byte and bit level. So in the past few lectures, we really did an in-depth discussion on this field here, which is the 11-bit identifier. It's the message identifier in the standard CAN packet, which is also responsible for network arbitration, especially with respect to non-destructive collision detection. The next thing that we have to look at is what you call the data field here. It's 0 to 8 bytes. Now, not as complicated as the 11-bit identifier. Data field, of course, would actually hold the relevant data based on the equipment in which the CAN network is installed. So, for instance, in a vehicle, you'll have things like oil temperature, oil pressure, you'll have door lock status, you'll have RPM, all of the many different types of data that'll be flying around in a car when communication is taking place. And of course, in a plane, it's going to be different data. In a boat, it's going to be similar, different data. So it's similar data, yet different. Now, here's the major point to remember with this data field here within the standard CAN packet. The CAN bus specification does not specify the content of the data bytes. CAN bus doesn't care what the engineer or designer puts into that field. It could be 1 or 2 or 3 or 4 bytes. And remember, in the previous lectures, we looked at the message identifier. So according to the message identifier, it will, you choose a particular message identifier and then you choose the bytes that go along with it. So for instance, if there's a message identifier coming from the body control module in a vehicle, then the bytes in there might signify door lock status or motor voltage, the door motor voltage if there's a sliding door. Now, CAN bus doesn't specify how to express it inside of here, whether to use an unsigned integers or floating point, how many bits to use, which bits to use, which bytes to use. It doesn't. The specification in here comes directly from the designer. So the designer of the CAN bus network must decide, based on the piece of equipment in which the CAN bus network is being installed, what goes into here on a per message identifier basis, because it's not just one format for all message identifiers. According to the message identifier that is used, this will determine the format that is used in here, and that is determined by the design engineer. The fact that CAN bus doesn't specify the content of the data bytes is a good thing and a bad thing at the same time. So it's a good thing in the sense that it gives a lot of flexibility to the engineer. It's a bad thing in the sense of standardization. So that's the data byte field essentially. So it's up to the engineer to determine what goes in here, because the CAN bus specification does not specify the number to use, well, except with the limits of 8 and the content and how the content is arranged. So that's the data byte field there. Thus far in this section, we have looked at the message identifier field and the data field. I will eventually get into the CRC field and ACK and EOF and control and all this stuff. But I've dumped a lot of theory on you already. It's time to get into some practical. It's time to get into some practical to seal that theory that you've gotten so far. Again, I will go through the rest of these fields here, but we need to get some practical in to seal in the theory, because we have to answer this question. So we say, so all that theory is nice, great, wonderful. But as a technician, as an engineer, what exactly the heck do I do practically to create a CAN bus network? If I am an engineer or technician working on a piece of equipment, designing a CAN bus network, what exactly do I do? What do I need to configure, to program? So let me tell you what I'm going to do. This is the last lecture in this section. In the next section, we're going to get really practical. We are going to use some hardware, program it, configure it to create a very simple CAN bus network. And let me give you a hint as to what you do to create that. Notice that these red lines were there throughout when in the previous lectures. I had these red lines here, but I wasn't mentioning anything. They were just doing nothing. These red lines underneath here represent what fields you have to mess with as an engineer or technician to get a CAN bus network working. You have to specify the message identifiers and the data and some control bits here. Now, usually in the control field here, you don't have to specify anything. Everything is specified. But we will go into this eventually. But what we're going to do in the next section is that we're going to build a simple CAN bus network by specifying message identifiers and the data field format. To create a CAN bus network, that's essentially what you have to do. That's essentially what engineers and technicians do who work on CAN bus networks. They specify the message identifiers and they specify the format of these data bytes per message identifier. And that's what we're going to do. This is the mess of wires and stuff on my workbench, and this is what we're going to be working with, right? This is a CAN bus training kit. I'll tell you much more about it, of course, in the next section, but essentially, this will be a node, this will be a node, and there'll be some wires, a pair of wires in between them, and we're going to get these two to quote-unquote talk CAN bus between them to exchange data. And then we're going to monitor that data transmission using something called CAN bus monitor here and see how that transmission is taking place. So this is what we're going to do in the next section. That's the end of this section. On to the next.